Hello everyone, my name is Pooi See from the School of Material Science and Engineering, Nanyang Technological University of Singapore. Today it is my pleasure to share with you our research on printable tactile sensors for soft electronics and soft robotics. Tactile sensors are very useful for human-machine interface. They receive physical information from the environment through the soft receptive devices, and tactile sensing can also provide responses through a haptics technology, for example, in soft actuator. Soft electronics can benefit from tactile sensing due to the ability of obtaining information from physical interaction from the environment. It could enhance safety with the users compared to just purely based on vision or audio. In addition, tactile sensing will allow us to achieve a smart interactive interface, such as creating a third living space in a vehicle. Tactile sensing are very useful in soft robotics. For example, in the soft gripper or manipulators, where various product sizes, shapes, and weight of the products can be picked up and manipulated with a delicate speed and response. It also provides value in training simulation, in which the training efficiency can be enhanced in a truly realistic environment. Furthermore, the use of soft robotics tactile sensing in teleoperation allows the applications in environments that are dangerous and uncomfortable for human beings. For example, in deep sea exploration, nuclear remediation, or mining applications. Certainly, soft robotics with tactile sensing are very useful in robotic surgery, for example, in a master-slave operation, where the haptics cue provides anatomy information and the interaction between the instrument and patients will enhance the precise surgeon operation. In the development of haptics technology, it requires the sensing input in tactile form, followed by signal processing and an output with a tactile feedback. Typically, the haptics technology rely on admittance control paradigm, in which the input and output are in the form of pressure, touch, or strain. We'll introduce for today the 4 different types of tactile sensing based on piezoresistive, capacitive, piezoelectric, and triboelectric. In the actuator, for soft robotics and soft electronics, we will evaluate the relaxed ferroelectric polymer actuator, the dielectric elastomer actuator, and the photothermal induced actuators. In one of our earlier work in realizing strain sensors, we have utilized crumpled graphene as the sensing material, incorporating cellulose fibril that serves to improve the mechanical property. Through a vacuum filtration method, a flexible nanopaper is formed that can be embedded into liquid PDMS that realize a stretchable nanopaper upon curing that allows the stretchability up to 100% strain. The piezoresistive sensing is demonstrated here, where the change in resistance can be measured systematically as a function of strain. Compared to the nanopaper without the crumpled graphene, the flexible nanopaper show a surge in the resistance without a systematic piezoresistive behavior. While if we change the crumpled graphene into carbon nanotube and silver nanowires, the sensing performance or sensitivity is not high. The strain gauge factor here is relatively high compared to other materials, and it can be used in wearable, for example, in a smart glove that has embedded with the strain sensor. However, the work is not utilizing any printing technology that can allow localized deposition and patterning. Moving forward, we have developed 3D printing technology for use in tactile sensing development. It has the advantage of rapid prototyping for both soft robotics and soft electronics, and it reduces the assembly in which casting of multiple components might be required. The two most commonly 3D printing technology are the fused deposition modeling (FDM) and the direct ink writing (DIW). Other methods include DLP, materials jetting, and SLS. Overall, the multi-materials component and multiple head printing can be applicable in FDM and DIW, in which material savings and environment-friendly materials can be used. In one of our work, we have demonstrated development of materials of suitable viscoelastic property for 3D printing using DIW. Over here, a capacitive touch sensor is being demonstrated using a 3D printable conductor onto curved substrate. As we can see here, the capacitance is stable as a function of strain up to 800%. This allows us to achieve a stretchable capacitive touch sensor using 3D printing. The on-off ratio of the capacitive sensor is relatively stable as a function of strain. This is because of the robust electrical connection between the mechanical disparate deformable surfaces. And the stretchable conductor is realized in the presence of an elastic printable conductor ink that comprises of metallic silver flakes. When we use just the metallic silver flakes, the stretchability can be sustained at 300% strain. However, the resistance will increase incrementally as a function of a cycling number. Therefore, the cycling stability of the conductor needs to be improved. In order to reduce the resistance increment as a function of cycling number, which is typically due to the separation of the metal fillers, we have introduced the presence of liquid metal in the form of nanoparticles. The nanoparticles has an encapsulated shell with a thin layer of 0.5 to 3 nanometer oxide shell, which can be broken upon stretching, releasing the liquid metal to connect between the metal fillers during stretching. Here, we can see that the addition of the liquid metal into the silver flake, silver particles, and silver nanoparticles. It has created a system that allows high stretching strain more than 600%. This synthesized stretchable conductor shows a good performance as a function of cycling number, giving a resistance increment of less than 4 times, as shown in figure D, when it's repetitively stretched up to 200% strain. At higher strain state, in figure F, there is a gap between the stretch state and the relaxed state. Nevertheless, the resistance is still relatively stable. The gap in the resistance is due to the irreversible loss of the electrical conductive pathway, which were not strongly anchored by the liquid metal. This stretchable conductor shows a very important achievement in terms of an extremely stretchable conductor with high conductivity. In the development of piezoelectric sensing, we have also developed 3D printable ink based on the ferroelectric polymer. The conductive electrode is made of PVDF TRFE with silver flakes with similar weight ratio in the presence of MEK solvent. The cross-section of the device is shown at the right SEM imaging. The fully 3D printed piezoelectric sensor provides an output voltage of 6 volt under a 60 Newton force by pressing. It also shows a current density of 2 microampere per centimeter square, thereby giving a maximum power density of 1.4 nanowatt per square centimeter at the optimum load resistance. The material shows a piezoelectric coefficient of 20 picocoulomb per Newton. Utilizing the 3D printable formulated ink, we would like to realize a kirigami-based piezoelectric tactile sensing in a non-protrusion manner. Typically, in a kirigami structure, upon stretching, there will be tilting out of plane. In order to avoid this issue, we have added horizontal shortcuts at 2 locations. One is without crossing the end of the vertical cuts, and the other is crossing the ends of the vertical cut. From the simulation, we can see that the structure 2 and structure 3, which has horizontal cuts at the end, is giving a different displacement compared to the one in structure 1 without the horizontal cuts. Structure 3 has about 6 times better displacement compared to structure 1 and 5 times better compared to structure 2. Using this approach of structure 3, where the vertical cuts are meeting the ends of the vertical line, we're able to achieve a non-protruding kirigami stretch sensor, where stretching strain up to 300% can be achieved, producing a stable voltage output for the 3D printable tactile sensor. With this, we can apply the tactile sensor onto wearables. For example, in this case, it is used for gait sensing, where heel strike and toe off can be monitored systematically as a function of frequency. Interestingly, it also shows variation in the voltage output waveform when there is a deviation in the heel strike and the mid-stance as well as the toe off. This will give us an opportunity to monitor gait variations, for example, due to Parkinson or other diseases. Next, we move into triboelectric tactile sensing using a highly stretchable polymer that can be 3D printable. This synthesized polymer has abundant dynamic hydrogen bond that allows dissipation of bond energy during stretching and dynamic bond breaking and association during the dynamic stretching and relaxing, which allows unfolding of the long polymer chain. The synthesis of the material is shown here, where an NCO-terminated prepolymer is prepared, followed by the grafting with HEMA group, realizing a HEMA-based polyurethane acrylate material after UV curing. The resultant material has abundance of hard segment-rich region that serves as thermally cross-linked that control the stiffness and elasticity of the elastomer. Meanwhile, the soft segment enhances the toughness and facilitates the self-healing. As we can see here, upon healing at 24 hours, it can recover the mechanical stress strain up to a certain percentage. This PUA material can be used as a negative triboelectric layer. Using the similar metrics by adding in silver flakes and liquid metal, we use it as a current collector for the triboelectric nanogenerator. As we can see in this performance of 40 Newton at 5 Hz, it can consistently provide an output voltage of 100 volts. As a function of increasing force, we can see that there is a systematic change in the voltage output, allowing it to be used as a tactile sensing. Apart from 3D printing, we also utilize inkjet printing of hydrogel to create an ionic patch matrix. In this work, we demonstrate a formulated inkjet printable ink and use the inkjet printing to create a coplanar interlocking diamond layout structure in order to suppress the strain-induced artifacts during dynamic touch sensing. The design allows the proximity sensing to be achieved, multiple touch, as well as gesture communication. As we can see here, the gel that comprised of PVA with salt and water allow us to make interlock diamond layout with a separator curated by a 3D printable PDMS. The coplanar structure enhances the fringing field projection and therefore improves the sensitivity of the touch sensing array. As demonstrated here, in the dynamic stretch and touch and dynamic bend and touch, the touch panel is functioning well. It is also working in a proximity sensing as shown in the bar chart, where the interlock diamond layout is providing higher sensitivity. When the touch panel is stretched up to 40% strain, about 47% sensitivity can be achieved. A high signal-to-noise ratio of 19 dB can be achieved under 20% dynamic strain. Now, I would like to discuss some of our efforts on flexible actuator. Among the ferroelectric material, the PVDF terpolymer serves as a very good relaxer ferroelectric property that has high dielectric constant, low dielectric loss, as well as high strain response. This is ideal to make it as a flexible actuator. In the fabrication of the actuator, the top-bottom electrode is sandwiching the active terpolymer layer that has been annealed at various temperatures. Due to the crystallization behavior, as shown here, when it's annealed at 110 degrees Celsius, the device is giving us the highest strain and highest output force as a function of electric field strength. This is corresponding to the improved Young's modulus due to the crystallization of the terpolymer. The terpolymer relaxed ferroelectric flexible actuator can be improved in performance when we insert an interlayer that is made of metallic silver nanowire. This can be achieved through a layer-by-layer coating or printing technology. As we can see here, with the introduction of a silver nanowire interlayer into the device structure, embedded within the relaxed ferroelectric polymer, we are able to improve the force output due to the enhanced Young's modulus of the stack. This work shows that the Young's modulus has a crucial impact on the force output. Another important mechanism for actuation is based on the dielectric elastomer actuator. In this approach, the Maxwell stress is incurred that leads to charge accumulation coming from the Coulombic force generated. Due to the restriction, there will be an increase in area or reduction in thickness, and both is governed by the dielectric strength and the Young's modulus. The dielectric elastomer actuator has the advantage of lightweight, low cost, high specific energy density, and fast response. However, it has the disadvantages of viscoelastic drift that leads to reduced response time and certainly deviation in the displacement. Therefore, in order to prevent the viscoelastic drift that is coming from local slipping and sliding of the polymer chains, we have hypothesized that adding polar crosslinker will improve or eliminate this issue. Over here, we have added the polar crosslinker of PEGDA into the PUA. As a result, the dielectric constant is enhanced as a function of amount of polar crosslinker added. The mechanical stress strain curve also shows a reduced hysteresis as a function of polar crosslinker addition. This leads to an actuator that has minimum displacement of just 0.09 mm with 15 weight% of polar crosslinker addition, and the response time has also been improved. The dielectric actuator can also benefit from the modification of the electrode using an ionic conductor. The ionic conductor will create an electric double layer that leads to charge accumulation and therefore enhance strain output. The ionic conductor can be realized using organohydrogel that is prepared based on a physical cross-linking method. This method achieves a stable solution state with an excellent pot life as well as reversible and self-healing ability. The polymeric gel has an ionic component at the side chain, for example, over here with the methyl methacrylate and the sulfur-propyl methacrylate potassium salt, we created a water-soluble polymer. Based on different weight% of MMA, we studied the thermal stability of this actuator. As we can see here, the ionic conductivity of the ionohydrogel can be improved with the optimum content of MMA. For the pure PSPMA, it contains excessive ionic side chain that increase the ion-ion Coulombic interaction, and therefore it gives the lowest conductivity. As we can see here, this ionohydrogel has a good thermal stability. The weight loss as a function of time is pretty much stable at about 80% when it's heated at 100 degrees Celsius. There is minimal water loss during this heating duration. Compared to the control hydrogel that is made of acrylamide, we can see that there is phase separation due to the segregation of salt in hydrogel. Meanwhile, for the ionohydrogel that we have prepared with 50% MMA, it shows a healing efficiency of 67%, while that of 25% of MMA achieve a 98% performance in 3 hours. This ionic conductor provides a good option for the dielectric actuator to function at high temperature. As a result, we can see that the strain retention can be maintained over 400 minutes when it's heated at 100 degrees Celsius, with the optimum performance achieved for MMA 25%. In summary, we have demonstrated that through the synthesis of electroactive material and formulation of the ink for printing technology, coupled with deformable conductor electrodes, tactile sensing and actuator can be achieved for soft electronics and soft robotics applications. We believe that the printing technology has much role to play in strain engineering and functionality of materials, especially when it's coupled with multi-component printing. With that, I'd like to thank you for your attention. I'd like to acknowledge my co-workers as well as the funding agency. Thank you.